What lies at the center of a galaxy? Is it a cradle of creation or a monster devouring everything? Inside every galaxy beats a heart made of darkness. What secrets are hidden? Where stars are born and time collapses, dare to enter. The place where gravity rules and light can't escape. This is not just the center of a galaxy, it's the beginning of everything. Let's go inside. What if I told you that the most powerful places in our universe aren't the most distant or the most violent, but the quietest centers that hold everything together? We often look outward toward the edge of the universe, toward the stars far away. But what if we look inward, toward the center, the heart? Imagine a quiet spiral galaxy turning slowly in space. Its arms stretch outward like a cosmic pinwheel, stars scattered across its surface like diamonds on black velvet. But our journey today isn't toward those outer reaches. Instead, we're moving inward, following the spiral's natural curve toward something deeper. Galaxies are not empty spirals. They have cores, and in those cores lie power, memory, and mystery. Tonight, we drift gently into the heart of a galaxy not to solve it, but to feel it. The center of a galaxy holds everything else in orbit. Without it, stars would scatter into the void. Planets would lose their paths. The very structure we recognize as a galaxy would dissolve. Yet these centers remain largely unseen, hidden behind veils of dust, revealed only through special instruments and patient observation. Our relationship with centers is profound. Think about it. A seed contains the blueprint for an entire tree. The nucleus of an atom holds its protons and neutrons. The human heart pumps blood to every cell in our bodies. Centers matter. They organize. They sustain. They define. And so it is with galaxies. Their centers are not empty spaces, but places of extreme density and significance. They are the gravitational anchors around which billions of stars revolve in cosmic dance that has continued for billions of years. When we look up at the night sky, we see individual stars seemingly scattered randomly across the darkness. But most of these stars belong to our own galaxy, the Milky Way. And all of them, including our Sun, orbit a common center, a place we cannot see with our eyes, yet one that silently shapes the path of every star in our sky. What creates this gravitational anchor? What lives in these dense, bright cores? Why do some galactic hearts pulse with energy while others remain quiet and dark? The answers take us to places where physics stretches to its limits, where stars crowd together so densely they could fill our solar system hundreds of times over, where black holes with masses of billions of suns sit in perfect stillness, where time itself seems to curve and bend. But this isn't a story of violent extremes. It's a meditation on centers, on the places that hold everything else together, on the quiet power that shapes galaxies from within. Consider for a moment how a galaxy is born. In the early universe, clouds of hydrogen gas began to collapse under their own gravity. As they collapsed, they began to spin, forming flattened disks with dense centers. The most massive stars formed near these centers, living brief but brilliant lives before exploding as supernovae, enriching the surrounding gas with heavier elements. New stars formed from this enriched material, and the cycle continued. Over billions of years, these processes shaped the galaxies we see today. And at the heart of this evolution were the galactic centers, growing ever more massive, ever more influential on the galaxy around them. As we journey inward, we'll discover that galactic cores are places of both incredible activity and surprising calm. They're ancient, some forming billions of years ago, when the universe was young. They're powerful, containing the mass of millions or billions of stars in a relatively small space. And they're mysterious, challenging our understanding of physics and astronomy. The light from distant galactic centers has traveled across space for millions or even billions of years to reach our telescopes. It carries with it the story of a time long past, a moment in cosmic history, preserved in photons that have journeyed across the vastness of space to reach us here, now. There's something poetic about that. The centers of galaxies shine so brightly that their light can traverse the cosmos and still be detected by our instruments. These are not just dense collections of matter, but beacons, cosmic lighthouses broadcasting their presence across the universe. Let your mind drift with us now as we spiral slowly inward, past the outer arms with their young blue stars, through the galactic disk with its mixture of stars, gas, and dust, deeper still, into regions where stars crowd together, where light grows more concentrated, where gravity strengthens its hold. The journey inward is also a journey backward in time. The stars near a galaxy's core are often older than those in the spiral arms. They've orbited the galactic center many times, witnesses to the slow evolution of their cosmic home. If stars could speak, what stories would these ancient ones tell? We're moving toward the heart of a galaxy, not to conquer it or claim it, but to witness it. To feel, for a moment, the quiet intensity at the center of cosmic spirals. To understand that even in the vastness of space, there are centers that hold everything together. Our journey begins now, as we turn our gaze inward and discover what waits at the heart of a galaxy. A place of extreme density and brightness. A place where stars live in crowded proximity. A place where, in many galaxies, something even more extraordinary waits, hidden behind veils of gas and dust, detectable only by its profound influence on everything around it. Welcome to the center. Welcome to the heart of a galaxy. There is a kind of ultimate calm in the center of a black hole, a stillness with infinite mass. The singularity at its heart represents a kind of cosmic full stop, a place where the familiar laws of physics reach their limits. Yet from this apparent endpoint come some of the most energetic phenomena in the universe. When matter falls toward the black hole, but hasn't yet crossed the event horizon. The supermassive black holes at galactic centers are not destroyers but architects. Their gravity helps shape the orbits of stars in the galaxy's central regions. The energy they release influences the rate and location of star formation throughout the galaxy. They are not disruptions in the cosmic order, but essential components of it. As our journey carries us ever deeper toward the galactic center, we approach not an abyss of chaos, but a well of profound order. The supermassive black hole waiting at the heart of the galaxy is not a monster to be feared, but a cornerstone to be understood. A silent giant whose influence extends far beyond its invisible boundary, shaping the visible galaxy we observe. These quietest giants in the universe speak not with light or sound, but with gravity. Their message carried across thousands of light years through the curved fabric of space-time itself. And in that silent conversation between black hole and galaxy, we glimpse one of the most extraordinary relationships in cosmic architecture, a partnership billions of years in the making. The motion we observe in the gas and dust of the galactic center speaks to the dynamic nature of galaxies themselves. Far from being static collections of stars, galaxies are living systems, constantly evolving, with material flowing inward and outward, being born and dying, and the central black hole growing and occasionally erupting in episodes of intense activity. Invisible to our eyes but revealed by the full spectrum of astronomical observations, these rivers of gas and dust are the lifeblood of galaxies, carrying the raw materials for new stars and planets from the outer regions to the center, and sometimes back out again. They connect the visible stars to each other and to the invisible black hole, creating a unified, interconnected system that is greater than the sum of its parts. As our journey continues, remember that beneath the apparent stillness of the galactic center lies constant motion. Beneath the darkness lies the glow of heated gas and dust. And beneath the seeming emptiness of space lies structure of extraordinary beauty and complexity. This is not chaos but a higher form of order, one that emerges from the interplay of gravity, radiation, magnetism, and the inherent properties of matter itself. Future observations, particularly with new generations of infrared and radio telescopes, promise to reveal even more about the heart of our galaxy. We may soon be able to directly image the shadow of the central black hole, observe in detail the gas falling into it, and track the orbits of stars passing within just a few light hours of its event horizon. These observations will not only teach us about our particular galaxy, but will provide insights into the physics of black holes and the evolution of galaxies throughout the universe. There is something profoundly moving about studying the center of the Milky Way. This is not some distant, unrelated object, but the core of our cosmic home, the gravitational anchor that holds our star, our planet, and everything we have ever known. The light we now receive from the galactic center began its journey 26,000 years ago, when humans were still in the Ice Age, painting on cave walls and developing the first complex societies. In a very real sense, the center of the Milky Way is a part of us, and we are a part of it. The atoms in our bodies were forged in stars that may have orbited the galactic center many times before our Sunday even formed. The gravitational field of the central black hole, extending outward through the galaxy, subtly influences the orbit of our Sunday, and thus the path of Earth through space. We may never visit the galactic center in person, but its influence permeates our existence. As we contemplate this connection, we realize that despite the dust that hides the galactic center from our direct view, despite the vast distance that separates us from it, the heart of the Milky Way is not truly hidden or distant. It is here with us, its gravity holding us in orbit, its past written into the composition of our bodies, its rhythms echoing in the motion of our Sunday through space. Our home has a heart, and even though we cannot see it with our eyes, we are part of its greater body, connected to it as surely as the stars that wheel around it in their ancient orbits. What emerges from this complexity is not chaos, but a rich tapestry of possibilities. A universe where galaxies, like living organisms, follow general patterns of development while maintaining their individuality. The strange hearts we observe are not aberrations, but variations on a theme, each representing one of the many possible paths a galaxy can follow through its long cosmic lifetime. There is a profound beauty in this diversity, in the realization that the basic ingredients of galaxies, stars, gas, dust, and dark matter can organize themselves into such a variety of structures. It speaks to the creativity inherent in physical laws, to the way that simple rules can generate endless complexity when allowed to play out across vast scales of space and time. As we contemplate these strange galactic hearts, we're reminded that our own Milky Way is just one example among hundreds of billions of galaxies, each with its own central region, its own history, its own character. Our galaxy is neither the smallest nor the largest, neither the most active nor the most quiescent. It is simply one thread in the vast cosmic tapestry, one heart beating among countless others in the cosmic symphony. Yet there is also something profoundly meaningful in this perspective. By understanding the range of possibilities, the diversity of forms that galactic centers can take, we come to better appreciate our own cosmic home. The heart of the Milky Way, with its relatively quiet black hole, its dense nuclear star cluster, its moderate rate of star formation, is the product of our galaxy's particular history, the specific path it has followed through billions of years of cosmic evolution. And in that specificity lies significance. For it is this particular galaxy, with this particular central region, and this particular evolutionary history, that gave rise to the Sunday, to Earth, and ultimately to us. We are the products not of a generic galaxy, but of this galaxy, our home among the stars, with its own unique heart beating at its center, setting the rhythm for the cosmic dance that makes our existence possible. What exactly are we looking at when we peer into the center of a galaxy? As our journey takes us deeper toward the galactic core, the stars begin to change. They grow more numerous, more crowded together, like a city becoming denser as we approach its downtown. A galaxy's core is technically called its nucleus, or its bulge, but these clinical terms hardly capture the majesty of what we're witnessing. What we're seeing is the gravitational heart of an entire stellar city, a place where millions or even billions of stars orbit in close proximity, bound together by forces so powerful they transcend our everyday understanding of physics. Imagine taking all the stars visible in Earth's night sky, some 4,000 or so. Now imagine cramming those stars into a space no larger than our solar system. That begins to approximate the stellar density found in many galactic cores. Stars that would normally be separated by light years now orbit just fractions of a light year apart, their ancient light blending together into a soft, continuous glow. But to truly understand what a galactic core is, we need to understand what it is not. It is not chaotic, despite its extreme density. It is not violent, despite the powerful forces at play. Rather, it is a place of ordered complexity, where gravity has had billions of years to arrange stars into stable orbits. In most spiral galaxies like our own Milky Way, the core appears as a bright, roughly spherical collection of stars at the center of the flatter disk. We call this the bulge, and it typically contains the oldest stars in the galaxy. These stars move in all directions, unlike the stars in the disk, which mostly rotate together around the center in an orderly fashion. The bulge of a spiral galaxy can vary greatly in size. In some galaxies, it dominates, creating what astronomers call an early type spiral, where the central bulge outshines the surrounding disk. In others, it's more modest, a small bright spot at the center of prominent spiral arms. And in some, called late type spirals, the bulge is almost non-existent, with the spiral structure extending nearly to the very center. If we were to look at elliptical galaxies instead, we would find that they are essentially all bulge, with no disk or spiral arms at all. These galaxies appear as smooth, featureless ellipses of light, their stars moving in random orbits throughout the galaxy, rather than in the organized rotation we see in spiral galaxies. But regardless of the galaxy type, the core shares certain characteristics. It is a place of extreme gravity, where stars move faster than they do in the outer regions. It is a place of high stellar density, where stars exist in much closer proximity than they do elsewhere. And it is often home to something even more extraordinary, which we'll explore later in our journey. The stars in a galaxy's core aren't just packed more densely, they're also different in character from the stars in the spiral arms. In the arms, we find many young, hot, blue stars, recently formed from the gas and dust that permeates these regions. But in the core, we predominantly find older, cooler, redder stars, some almost as old as the universe itself. These ancient stars have been orbiting the galactic center since the galaxy's early days, billions of years ago. This is one of the most fascinating aspects of galactic cores. They are in many ways time capsules, preserving stars from the galaxy's earliest epochs. When we look at the center of a galaxy, we're looking at some of the first stars that formed within it. Stars that have witnessed the galaxy's entire history, from its tumultuous youth to its more settled present. The motion within a galactic core is equally fascinating. Stars here don't move in simple circular orbits, like planets around a sun. Instead, their paths are complex, often highly elliptical, and influenced by the combined gravity of all the other stars around them. Some stars plunge toward the very center before being flung back outward again. Others trace more circular paths. All are part of a gravitational ballet that has continued, uninterrupted, for billions of years. This motion creates something remarkable, a kind of cosmic stability through continuous change. Individual stars may move in seemingly chaotic ways, but the overall structure of the core remains stable over timescales so vast they dwarf human history. There is a profound lesson here about how order can emerge from complexity when given enough time and space. As we drift closer to the center of our hypothetical galaxy, we begin to notice the very center isn't just bright with stars. There's often a single point of intense brightness, a nucleus within the nucleus. This is where things get truly extraordinary, for at the very center of most large galaxies lies something both invisible and enormously influential, a supermassive black hole. But the black hole isn't alone at the center. Surrounding it is often a dense cluster of stars, gas, and dust, all orbiting this invisible giant at tremendous speeds. This central region, sometimes just a few light years across, can outshine all the rest of the galaxy, combined if the black hole is actively feeding on surrounding material. The interplay between the stars of the bulge and the central black hole is one of the most fascinating aspects of galactic evolution. Evidence suggests that galaxies and their central black holes grow together, each influencing the other's development through complex feedback mechanisms that astronomers are still working to fully understand. Not all galactic cores are created equal. Some are quiet, their central black holes dormant, surrounded by old stars, slowly orbiting in stately procession. Others are active, their centers blazing with the light of gas heating to extreme temperatures as it falls toward the central black hole. These active galactic nuclei, or AGN, can be some of the brightest objects in the universe, visible across billions of light years. Even the shape of the core can vary. Some are nearly spherical, others flattened into disks, and still others elongated into bar shapes that extend outward from the center, connecting to the spiral arms. These bars, found in many spiral galaxies including our own Milky Way, act as gravitational highways, channeling gas from the outer regions toward the center, potentially feeding the central black hole and triggering bursts of star formation. What's remarkable about all this complexity is how it emerges from simple physical laws, gravity being key among them. The intricate structure and behavior of galactic cores is what happens when gravity is given billions of years to shape the trajectories of trillions of stars, all influencing each other in an incomprehensibly complex web of mutual attraction. As our journey continues inward, remember that what we're witnessing isn't chaos but concentrated order, not random movement, but the culmination of billions of years of gravitational evolution. Every spiral has a source, and in the heart of a galaxy, we find that source. A place where stars, gas, dust, and even light itself converge in a cosmic focal point of extraordinary beauty and power. As we continue our journey deeper into the galactic heart, let us focus now on its primary residence, the stars themselves. The stars that populate a galaxy's center are unlike those found in the spiral arms. They tell a different story, one of ancient origins and patient endurance. Most of the stars in a galactic bulge were born long ago, in the earliest epochs of galaxy formation. While the spiral arms continue to form new stars even today, the central regions largely completed their star formation billions of years in the past. What we see when we look at a galactic center are the survivors, stars that have lived for billions of years, witnessing the entire history of their galaxy. These central stars are predominantly what astronomers call population 2 stars, an older generation of stars formed when the universe contained fewer heavy elements. By contrast, our Sunday is a population 1 star, born much later in cosmic history, after previous generations of stars had enriched the galaxy with elements heavier than hydrogen and helium. The stars in the galactic center are packed with extraordinary density. In our solar neighborhood, stars typically lie several light years apart, but in the galactic center, this distance shrinks dramatically. Stars may be separated by just a fraction of a light year, or even less in the densest central clusters. If Earth orbited a star in such a region, our night sky would blaze with thousands of stars bright enough to cast shadows, creating a perpetual twilight, even in the absence of our own sun. This incredible stellar density creates a visual spectacle, unlike anything we can observe from Earth. Imagine stars so numerous they seem to merge into a continuous glow, their individual identities lost in a sea of collective light. From within such a region, the concept of night would be meaningless. There would always be starlight coming from all directions, a cosmic dome of perpetual illumination. Many of the stars in galactic centers are red giants, stars in the late stages of their lives that have swollen to enormous sizes. These aging stars have exhausted the hydrogen in their cores and now burn helium, causing them to expand and cool, taking on a distinctive reddish hue. Their presence gives many galactic bulges a noticeably redder color compared to the bluer spiral arms. A red giant star can be hundreds of times larger than our Sunday. If placed at the center of our solar system, such a star would engulf Mercury, Venus, Earth, and possibly even Mars. Yet despite their imposing size, red giants are relatively cool, with surface temperatures around 3,000 degrees Celsius. compared to the Sun's roughly 5,500 degrees. These ancient giants move with surprising grace through the crowded central regions. Their orbits are not circular, but elliptical, taking them sometimes closer to the very center, other times farther away. Over billions of years, interactions with other stars have randomized these orbits, creating a three-dimensional ballet where stars move in all directions rather than in the organized rotation we see in the galactic disk. Alongside the red giants are smaller, longer-lived stars similar to our Sun, but generally older. These main sequence stars steadily burn hydrogen in their cores, living stable lives that can last for billions or even trillions of years for the smallest among them. Some of these stars may have planetary systems, though the crowded environment and frequent close encounters with other stars make stable planetary orbits more challenging to maintain than in the galactic outskirts. In the very center, surrounding the supermassive black hole, we often find an even denser concentration of stars called a nuclear star cluster. These remarkable objects can contain millions of stars packed into a region just a few light years across. For comparison, the nearest star to our Sun, Proxima Centauri, is over 4 light years away. In a nuclear star cluster, thousands of stars might exist within that same volume. The stars in these central clusters live dangerous lives. They orbit the central black hole at tremendous speeds, sometimes thousands of kilometers per second. Close encounters with other stars are common, leading to complex gravitational interactions that can fling stars outward or draw them inward toward the waiting black hole. Some stars are torn apart by the black hole's tidal forces, creating brief but spectacular flares of radiation as their material is stretched, heated, and eventually consumed. Despite this seemingly chaotic environment, the nuclear star cluster as a whole maintains a stable structure over long timescales. Individual stars may come and go, but the cluster persists, shaped by the powerful gravity of both the central black hole and the collective mass of the stars themselves. One of the most fascinating aspects of these central stars is their age. Many formed over 10 billion years ago, when the universe was less than a quarter of its current age. These ancient stars have completed hundreds or even thousands of orbits around the galactic center, witnessing the evolution of their galaxy from its tumultuous youth to its more settled present. If stars could speak, what tales these elders might tell. They might describe the early galaxy, perhaps more disordered and active than it is today. They might recount close encounters with other stars, or the gradual growth of the central black hole. They might even remember the last major merger with another galaxy, an event that would have dramatically reshaped the galaxy's structure and triggered bursts of new star formation. While most galactic centers are dominated by old stars, some galaxies break this pattern. In some spiral galaxies, we find evidence of recent or ongoing star formation right at the center. These starburst nuclei, as astronomers call them, are regions where new stars are being born at rates hundreds of times higher than in our Milky Way. What triggers such intense central star formation? Often, it's the result of interaction with another galaxy. When galaxies pass close to each other or begin to merge, gravitational forces can funnel gas toward their centers. This concentrated gas becomes the raw material for new stars, igniting a burst of stellar birth in a region typically dominated by ancient stars. These central starbursts create a remarkable contrast, young blue stars forming and living their brief, brilliant lives amongst the older red population. The youngest and hottest stars in these regions emit intense ultraviolet radiation, causing surrounding gas to glow with the characteristic red light of hydrogen emission. This creates spectacular rosettes of glowing gas around the hot young stars, visible even across millions of light years. But such bursts of central star formation are generally short-lived on cosmic timescales, lasting perhaps a few 100 million years before the gas supply is exhausted. Once the burst ends, star formation slows or stops entirely, and the center returns to its more typical state, dominated by older stars. In some galaxies, we find another type of stellar population at the center: globular clusters. These densely packed spherical collections of hundreds of thousands of stars orbit in the halo of their galaxy, but are often concentrated toward the center. Like the stars in the bulge, globular cluster stars are ancient, among the oldest objects we can observe in the universe. Some globular clusters may actually be the remnant cores of smaller galaxies that were consumed by the larger galaxy, their outer stars stripped away while their dense centers survived as compact star clusters. The stars at a galaxy's center have witnessed the entire history of their cosmic home. They are the keepers of galactic memory, their orbits and compositions preserving information about events long past. By studying these stars, astronomers can reconstruct a galaxy's history, learning about its formation, evolution, and interactions with other galaxies. There is something profoundly moving about these ancient central stars. In a universe often characterized by violence and change, they represent stability and endurance. Many have shone for billions of years and will continue to shine for billions more. They burn with a steady, patient light, neither bright nor flashy, like their younger counterparts in the spiral arms, but constant, reliable, present. As our journey continues inward, toward the very center of the galaxy, we carry with us this image of ancient stars in their stately orbits, a living shell of light surrounding the still greater mystery waiting at the very core. These stars are both the witnesses and the guardians of the galactic center, their collective gravity helping to shape and maintain the heart of their cosmic home. They remind us that at the center of seeming chaos often lies profound order, and that some of the most powerful forces in the universe express themselves not through destruction, but through patient, enduring creation. The density of memory embodied in these stars speaks to us across the void, telling a story of cosmic time beyond human comprehension, yet somehow still resonant with our own brief experience of existence. We have journeyed past the ancient stars of the galactic bulge, through the dense nuclear star cluster, and now we approach the very center, the true heart of the galaxy. Here lies one of the most extraordinary objects in the universe, a supermassive black hole. The term itself carries weight, even gravity. Supermassive black hole. Each word matters. These are not merely black holes like those that form from collapsed stars. They are supermassive, containing the mass of millions, sometimes billions of suns, compressed into a region smaller than our solar system. What does it mean to say that almost every large galaxy harbors one of these giants at its core? It means that these objects, once thought to be rare cosmic anomalies, are instead fundamental components of galactic architecture. They are not invaders or interlopers, but integral parts of the galaxies they inhabit, co-evolving with their hosts over billions of years. Despite their enormous influence, supermassive black holes themselves are invisible. A black hole has no solid surface that reflects light. What it has instead is an event horizon, a boundary in space-time beyond which nothing, not even light, can escape. For a supermassive black hole with the mass of 4 million suns, like the one at the center of our Milky Way, this event horizon would be roughly 17 times the size of our Sunday, yet contain a mass millions of times greater. How do we know these invisible giants exist? We see their gravitational effects on surrounding stars and gas. Stars near the galactic center orbit something massive yet unseen, moving at speeds that can only be explained by the presence of an object containing millions of solar masses, concentrated in a very small volume. The only known object that fits this description is a supermassive black hole. At the center of our own galaxy lies such a black hole, given the name Sagittarius A star. This cosmic giant contains the mass of approximately 4 million suns. Yet despite this enormous mass, it's currently quiet, not actively consuming large amounts of material. If it were not for its gravitational influence on nearby stars, we might not know it exists at all. This points to something counterintuitive about supermassive black holes. Despite their fearsome reputation, they are not cosmic vacuum cleaners, inexorably drawing in all nearby matter. They are more like anchors, their enormous gravity helping to stabilize the galaxy around them. Stars can orbit a black hole, just as planets orbit the Sunday, provided they maintain sufficient distance from the event horizon. The origin of these cosmic giants remains one of astronomy's greatest puzzles. How did objects so massive form in the early universe? Some may have grown from smaller black holes created by the first generation of massive stars. Others might have formed directly from the collapse of enormous clouds of gas in the young universe. bypassing the stellar stage entirely. Still others could be the result of mergers between smaller black holes, gradually building up to their current enormous sizes. Whatever their origins, supermassive black holes appear to grow alongside their host galaxies, their masses often correlating with properties of the galaxy as a whole. There seems to be a deep connection between these central giants and the larger stellar systems they inhabit, a cosmic feedback loop, where the evolution of one influences the evolution of the other. Most of the time, supermassive black holes are relatively quiet. They exert their gravitational influence on surrounding stars and gas, but they aren't actively consuming large amounts of material. The black hole at the center of our Milky Way is in such a quiescent state, detectable primarily through its gravitational effects on nearby stars. But occasionally, something disrupts this quiet existence. A cloud of gas might fall toward the black hole, or a star might wander too close, torn apart by tidal forces. When this happens, the material doesn't simply fall directly into the black hole. Instead, it forms an accretion disk, a flattened ring of gas spiraling inward. As this material orbits ever closer to the event horizon, friction causes it to heat up, eventually reaching temperatures of millions of degrees. At such temperatures, the gas glows brightly across the electromagnetic spectrum, from radio waves to X-rays. The inner regions of this accretion disk can outshine all the stars in the galaxy combined, creating what astronomers call an active galactic nucleus, or AGN. The most extreme examples of active galactic nuclei are quasars, objects so bright they can be seen across billions of light years. A typical quasar might emit the light of 1 trillion suns from a region no larger than our solar system. This incredible luminosity comes not from the black hole itself, which emits no light, but from the superheated gas in the accretion disk, and from powerful jets of particles ejected perpendicular to the disk. These jets are another fascinating aspect of active supermassive black holes. For reasons still not fully understood, some actively feeding black holes launch streams of particles away from their poles at speeds approaching that of light. These relativistic jets can extend for hundreds of thousands of light years, far beyond the galaxy itself, creating some of the largest coherent structures in the universe. The energy output of an active supermassive black hole can profoundly influence its host galaxy. The radiation and particle jets can heat surrounding gas, preventing it from cooling enough to form new stars. This process, called AGN feedback, is thought to play a crucial role in regulating star formation in massive galaxies, potentially explaining why such galaxies tend to contain older stellar populations. But these active phases are generally temporary. Once the available gas near the black hole is consumed or dispersed, the black hole returns to a quieter state. This cycle may repeat many times throughout a galaxy's history, whenever new material becomes available for the black hole to consume. It's worth pausing to consider the profound paradox embodied by supermassive black holes. They are simultaneously the simplest and most complex objects in the universe. Simple, because a black hole can be completely described by just 3 parameters: its mass, electric charge, and rotation. All other information about what formed the black hole is lost, a property physicists call the no-hair theorem. Yet black holes are also sites of extreme complexity, places where our current understanding of physics breaks down. At the center of a black hole lies a singularity, a point where matter is compressed to infinite density and space-time curvature becomes infinite. Our current physical theories cannot describe what happens at such a singularity, suggesting there is deeper physics yet to be discovered. Black holes also exist at the intersection of general relativity, Einstein's theory of gravity, and quantum mechanics, the theory of the very small. These 2 pillars of modern physics are known to be incompatible in their current forms, and nowhere is this incompatibility more apparent than in the physics of black holes. The quest to reconcile these theories, to develop a quantum theory of gravity, is one of the great scientific challenges of our time. Despite being named for darkness, black holes have illuminated some of the most profound questions in physics. They have been theoretical laboratories for exploring the nature of space, time, and gravity. They have challenged our understanding of information and entropy. They have even provided insights into the possible existence of other universes. Yet for all their exotic physics, supermassive black holes are also integral parts of the galaxies they inhabit. Their growth appears tied to the growth of their host galaxy. Their activity influences star formation throughout the galaxy. Far from being isolated curiosities, they are dynamic participants in galactic evolution. There is something almost poetic about these cosmic giants. Despite containing millions or billions of solar masses, they occupy a volume that is, on galactic scales, vanishingly small. They are simultaneously the most massive and the most compact significant objects in their galaxies. They exert enormous influence while remaining, in themselves, invisible. The stillness of a supermassive black hole contrasts sharply with the frantic activity that sometimes surrounds it. The black hole itself neither emits nor reflects light. It simply is, a region of space-time so curved that paths lead inexorably inward. Yet around it, matter can be heated to millions of degrees. Magnetic fields can accelerate particles to nearly the speed of light, and energy can be released at rates that dwarf the combined output of every star in the galaxy. As we contemplate these cosmic giants, there's a natural tendency to anthropomorphize, to attribute to them characteristics like hunger or violence. But a black hole is not alive. It does not desire or seek to consume. It simply exists, its enormous gravity an inevitable consequence of its mass. Stars and gas fall into black holes not because black holes are reaching out to grab them, but because matter follows the curvature of space-time. And near a black hole, all paths curve inward. As we continue our journey into the galactic core, we discover that stars are not the only residents of this crowded realm. Between the stars flows an intricate network of gas and dust, invisible to our eyes but revealed by specialized telescopes. This interstellar medium, as astronomers call it, is not merely empty space, filled with scattered particles. It is a dynamic, structured environment, constantly in motion, shaped by gravity, radiation, and magnetic fields. In the central regions of a galaxy, this gas and dust exists in higher concentrations than in the outskirts. Rivers of molecular hydrogen, the most common molecule in the universe, flow through the galactic center, sometimes forming dense clouds, where new stars might one day be born. Alongside the hydrogen are other gases, helium primarily, but also trace amounts of more complex molecules, some surprisingly similar to those found on Earth. Interspersed with the gas are tiny solid particles, cosmic dust grains typically less than a micrometer in size, smaller than the wavelength of visible light. Despite their minuscule dimensions, these dust grains play an outsized role in the physics and appearance of the galactic center. They absorb and scatter light, particularly in the blue part of the spectrum, causing the light from stars behind them to appear redder than it actually is, a process astronomers call reddening. This dust is not the household variety we might find under a bed, but a mix of silicates, similar to minerals found in Earth rocks, and carbonaceous materials, related to graphite and coal. Some dust grains may even have ice mantles, microscopic coatings of frozen water, carbon dioxide, or methane. Each grain is a tiny world, with its own complex chemistry and structure. The gas and dust near a galaxy's center don't simply float in space. They move, driven by a variety of forces. Most fundamental is gravity, pulling material toward the center, toward the supermassive black hole. But gravity isn't the only force at play. Radiation from stars pushes outward, particularly on the lighter dust grains. Magnetic fields thread through the gas, constraining its motion like invisible rails. And the collective effects of stellar winds, radiation pressure, and occasional supernova explosions can drive material outward, sometimes fast enough to escape the galaxy entirely. The result of these competing forces is not chaos, but a complex, ordered flow. Gas near the center often forms a disk, rotating around the supermassive black hole. In some cases, this circumnuclear disk, as astronomers call it, can extend for hundreds of light years. Within this disk, gas moves in roughly circular orbits, but with superimposed turbulent motions that cause it to swirl and eddy on smaller scales. The motion of this central gas can reach astonishing speeds. Near the supermassive black hole, gas can orbit at thousands of kilometers per second, a significant fraction of the speed of light. Such rapid motion heats the gas through friction, causing it to glow brightly across the electromagnetic spectrum, from radio waves to X-rays. This hot, glowing gas near the center creates some of the most spectacular phenomena associated with galactic nuclei. In active galaxies, it forms the accretion disk around the central black hole, a flattened ring of material spiraling inward. As it falls closer to the event horizon, the gas heats to millions of degrees, emitting intense radiation that can outshine all the stars in the galaxy combined. Not all the gas falls into the black hole, however. In many active galaxies, some of the superheated gas is launched outward in powerful jets, perpendicular to the accretion disk. These jets can extend for hundreds of thousands of light years, far beyond the visible boundaries of the galaxy itself. They are among the most energetic phenomena in the universe, accelerating particles to speeds approaching that of light. The dust near a galactic center plays a different but equally important role. Because dust grains absorb visible light, but are transparent to infrared, they effectively veil the galactic center when viewed with optical telescopes. This is why the center of our own Milky Way, despite being only about 26,000 light-years away, remained mysterious until the development of infrared and radio astronomy. This veiling effect creates a kind of cosmic irony. The most energetic, active regions in many galaxies are hidden from direct view by curtains of dust. We can see their effects, the radiation they produce after it has been reprocessed by the surrounding material, but not the central engines themselves. It's as if nature has drawn a veil over some of its most extreme environments, revealing them only indirectly through their influence on surrounding space. But dust doesn't just obscure, it also glows. Heated by the radiation from nearby stars or the central black hole, dust grains emit infrared radiation, appearing as warm halos around hot stars or as extended clouds throughout the galactic center. This infrared emission allows astronomers to map the distribution of dust, even when it's too diffuse to be visible in other ways. The interplay between gas, dust, and radiation creates complex structures within the galactic center. In some regions, the intense radiation from young hot stars or from the central black hole can carve bubbles in the surrounding medium, pushing gas and dust outward to form shells or arcs. In others, the gravitational influence of the black hole or of massive star clusters can pull material inward, creating dense filaments or streams. These structures are not static, but ever-changing. The timescales for this change are long by human standards, thousands or millions of years, but brief in cosmic terms. Over time, clouds collide and merge, bubbles expand and dissipate, and streams of gas are diverted by the gravitational influence of stars or star clusters they encounter on their journey. In some galactic centers, the gas and dust are relatively quiescent, moving in stable orbits, neither falling rapidly inward nor being expelled outward. In others, there is dramatic activity, with gas flowing inward to feed the central black hole or being ejected outward in powerful outflows driven by the energy released during this feeding process. This activity can have profound effects on the galaxy as a whole. The energy released by an actively feeding black hole can heat gas throughout the galaxy, preventing it from cooling enough to form new stars. This process, called AGN feedback, is thought to play a crucial role in regulating star formation in massive galaxies, potentially explaining why such galaxies tend to contain older stellar populations. The flow of gas inward can also trigger bursts of star formation near the galactic center. When gas is compressed, whether by the gravitational influence of the black hole, by collision with other gas clouds, or by the pressure of surrounding hot gas, it can reach densities high enough for gravity to overcome other supporting forces, leading to collapse and the formation of new stars. These central starbursts, as astronomers call them, can be spectacular, forming stars at rates hundreds of times higher than in more quiescent galaxies like our Milky Way. The most massive of these new stars live brief but brilliant lives, ending in supernova explosions that further stir the surrounding medium, potentially triggering additional star formation in a self-propagating cycle. The dust in the galactic center also plays a role in star formation. Dust grains serve as catalysts for the formation of molecular hydrogen, the primary fuel for star formation. They also shield molecules from the harsh ultraviolet radiation that would otherwise break them apart, allowing dense molecular clouds to form and persist long enough to collapse into new stars. The motion of gas and dust near the galactic center is not solely inward or outward, but often follows more complex paths. In many spiral galaxies, including our Milky Way, the central regions contain a bar, an elongated structure of stars and gas that rotates like a rigid body. This bar creates non-circular orbits for gas, funneling it inward toward the center, along specific pathways. These flowing rivers of gas can feed both star formation and the central black hole, providing the raw material for both processes. The balance between these destinations, how much gas forms new stars versus how much falls into the black hole, can vary greatly from galaxy to galaxy, and even within the same galaxy over time. What emerges from all this complexity is a picture of the galactic center as a place of continuous flow and transformation. Gas falls inward, is heated and compressed, forms stars or feeds the central black hole, and some is then expelled outward again in stellar winds, supernova explosions, or black hole-driven outflows. Dust absorbs light from stars and the central regions, is heated, and re-emits that energy as infrared radiation, visible to specialized telescopes. There is beauty in this turbulence, in the swirling patterns of gas illuminated by starlight, in the delicate filaments of dust silhouetted against the bright background of distant stars. What might appear chaotic at first glance reveals itself, upon closer examination, to be a system of remarkable order and structure, shaped by forces operating across vast scales of space and time. After our journey through the general features of galactic cores, let us now turn our gaze homeward, to the heart of our own cosmic neighborhood, the center of the Milky Way. This is not a distant, abstract concept, but the gravitational anchor of our cosmic home, the center around which our sun, our planet, and everything we have ever known orbits once every 230 million years. The center of the Milky Way lies approximately 26,000 light-years from Earth, in the direction of the constellation Sagittarius. From our perspective embedded within the galactic disk, this central region is largely hidden from view in visible light, obscured by thick clouds of dust that absorb and scatter the light from stars beyond. This veil of cosmic dust has kept the secrets of our galactic center well hidden throughout most of human history. Only with the advent of telescopes that can see beyond visible light, particularly in the infrared, radio, and X-ray parts of the spectrum, has the heart of our galaxy begun to reveal itself. What these observations show is a region of extraordinary complexity and activity, a worthy center for a galaxy containing hundreds of billions of stars. At the very core of the Milky Way lies an object designated Sagittarius A star, often abbreviated as SCAR A star. This is a compact radio source that marks the location of our galaxy's supermassive black hole. Unlike the dramatically active black holes in some other galaxies, our central black hole is relatively quiet at present, not actively consuming large amounts of material. But its gravitational influence is unmistakable, causing stars in its vicinity to orbit at tremendous speeds. The mass of this central black hole has been measured with remarkable precision by tracking the orbits of stars around it over many years. These observations reveal a mass of about 4 million times that of our Sun, all concentrated in a region smaller than our solar system. This is substantially smaller than the black holes found in many large elliptical galaxies, which can contain billions of solar masses. But it is still an object of extraordinary density and gravitational influence. Surrounding Sagittarius A star is a dense cluster of stars, the nuclear star cluster of the Milky Way. This remarkable stellar collection contains millions of stars packed into a region just a few dozen light-years across. If Earth were located within this cluster, our night sky would blaze with thousands of stars bright enough to cast shadows, creating a perpetual twilight even in the absence of the Sun. Many of the stars in this central cluster are old, having orbited the galactic center for billions of years. But surprisingly, Astronomers have also found many young, massive stars there, some only a few million years old. Their presence poses a puzzle because the intense gravitational forces near the supermassive black hole should make it difficult for new stars to form. Yet somehow, star formation has occurred recently in this extreme environment. One possibility is that these young stars formed elsewhere and migrated inward. Another is that they formed in place during a period when gas near the center was compressed by some event, perhaps a collision between molecular clouds or the gravitational influence of the black hole itself. Whatever the mechanism, their presence reminds us that the galactic center is not a static place, but one where creation continues, even in the shadow of the central black hole. Beyond the nuclear star cluster lies the galactic bulge, a roughly spherical collection of stars, a few thousand light-years in diameter. The stars in the bulge are predominantly old, many having formed in the early days of our galaxy's history, over 10 billion years ago. They move in random orbits, unlike the stars in the disk, which orbit in a more organized fashion around the center. The bulge of the Milky Way is now known to contain a bar structure, an elongated distribution of stars that rotates like a rigid body. This bar, extending thousands of light-years from the center, influences the orbits of stars and gas throughout the inner galaxy, helping to maintain the spiral structure we observe and channeling gas inward toward the central regions. Between the stars of the bulge flows a complex network of gas and dust. Near the very center, within the central few light-years, astronomers have identified a remarkable structure called the circumnuclear disk, a ring of molecular gas orbiting the central black hole. This disk contains enough gas to form thousands of new stars and may someday provide fuel for renewed activity from the central black hole. Farther out, but still within the central few hundred light-years, lie massive clouds of molecular hydrogen, the raw material from which new stars form. These central molecular zone clouds, as astronomers call them, are unlike molecular clouds elsewhere in the galaxy. They are denser, more turbulent, and subject to stronger magnetic fields. Despite containing enough gas to form millions of stars, they form stars at a surprisingly low rate, perhaps held back by the turbulent motion within them. The central regions of the Milky Way are also home to some of the most massive star clusters in our galaxy. The arches and quintuplet clusters, located just a few dozen light-years from the center, contain hundreds of massive stars, including rare Wolf-Rayet stars and luminous blue variables, some of the most massive and short-lived stellar types known. These clusters are only a few million years old, providing further evidence of recent star formation near the galactic center. One of the most striking features of the Milky Way's center, visible primarily in radio and X-ray observations, are the so-called Fermi bubbles, enormous lobes of energetic gas extending about 25,000 light-years above and below the galactic plane. These structures, discovered relatively recently, appear to be the result of some energetic event at the galactic center, perhaps a period of intense activity from the central black hole or a burst of star formation and subsequent supernovae. The timescale of this event is uncertain, occurring perhaps a few million years ago, a mere moment in cosmic terms, but long before human civilization. These bubbles remind us that while the center of our galaxy appears relatively quiet now, it has not always been so, and may not remain so in the future. Indeed, observations of small clouds of gas near Sagittarius A star suggest that our central black hole may have been much more active just a few hundred years ago. The glow of these clouds appears to be an echo of past activity, light emitted when the clouds were illuminated by a flare of radiation from the black hole, now long since faded from our direct view. The magnetic fields near the center of our galaxy are another remarkable feature. Radio observations reveal a complex network of magnetic filaments, some extending hundreds of light-years, oriented perpendicular to the galactic plane. The origin of these filaments remains uncertain, but they testify to the presence of strong, organized magnetic fields in the central regions, fields that likely play an important role in regulating the flow of gas and the formation of new stars. From our perspective, some 26,000 light-years away, we cannot directly observe the very center of our galaxy in visible light. The dust that fills the galactic disk absorbs nearly all the visible light from the central regions, allowing less than 1 photon in a trillion to reach us. This is why the center of the Milky Way remains invisible to the naked eye, despite containing millions of stars and being intrinsically very bright. This obscuration has, in many ways, shaped our understanding of our cosmic home. Ancient civilizations, looking up at the night sky, could see the band of the Milky Way stretching across the heavens, but had no way of knowing that our Sunday was just one of billions of stars orbiting a common center. Only in the 20th century, with the development of radio astronomy and the realization that the Milky Way is a spiral galaxy similar to others observed in the distant universe, did the true nature of our cosmic surroundings become clear. Now, with infrared telescopes capable of piercing the dust and revealing the stars behind, we can finally see into the heart of our galaxy. What these observations show is both familiar and alien, a region recognizable as a galactic center, with features common to many galaxies, yet also unique in its specific structure and history, a product of our galaxy's particular evolutionary path. The center of the Milky Way is also a laboratory for testing our theories of physics under extreme conditions. The stars orbiting close to Sagittarius, a star moved through stronger gravitational fields and at higher speeds than objects anywhere else we can observe in detail. Their orbits have already provided some of the strongest evidence for the existence of the central black hole, and have allowed tests of Einstein's general theory of relativity in a regime of strong gravity far beyond what we can probe in our solar system. Just as no two human hearts beat exactly alike, no two galactic hearts are identical. Across the vastness of cosmic space, telescopes have revealed an astonishing diversity of galactic centers, each with its own character, its own story, its own rhythm. In this chapter, we explore galaxies with particularly unusual or extreme central regions, places where nature has crafted variations on the theme of galactic hearts. Perhaps the most dramatic of these are galaxies with active galactic nuclei, or AGN. These are galactic centers where the central supermassive black hole is actively feeding on surrounding material, creating a display of energy that can outshine all the stars in the galaxy combined. Unlike the relatively quiet black hole at the center of our Milky Way, these active black holes announce their presence across billions of light years. When gas falls toward a supermassive black hole, it doesn't simply drop straight in. Instead, it forms a rapidly spinning accretion disk, heated by friction to temperatures of millions of degrees. This superheated gas glows brightly across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. The inner regions of this disk can be so bright that they outshine 1 trillion suns, all from a region no larger than our solar system. The most extreme examples of active galactic nuclei are quasars, objects so luminous they can be seen across most of the observable universe. The term quasar comes from quasi-stellar radio source, reflecting the fact that when first discovered, these objects appeared star-like in optical telescopes, but were powerful sources of radio emission. We now know that quasars are the extremely bright centers of distant galaxies, powered by supermassive black holes consuming material at tremendous rates. Quasars were more common in the early universe than they are today. Billions of years ago, when galaxies were younger and contained more gas, many galactic centers went through quasar phases, their central black holes growing rapidly as they consumed the abundant material around them. As this fuel supply dwindled, most quasars eventually quieted down, leaving behind the more sedate galactic centers we typically observe in the nearby universe. But active galactic nuclei come in many forms besides quasars. Seyfert galaxies, for instance, have bright, star-like nuclei. But, unlike quasars, their host galaxies are clearly visible. These represent a less extreme form of nuclear activity, where the central black hole is still actively feeding, but at a lower rate than in quasars. Seyfert galaxies are relatively common in the nearby universe, suggesting that many galaxies go through phases of moderate nuclear activity. Another type of active galactic nucleus is the blazar, where we happen to be looking down the barrel of a powerful jet of particles ejected from the vicinity of the black hole. These jets, accelerated to speeds approaching that of light, are a common feature of many active galactic nuclei, but in most cases, they point in directions other than toward Earth. When a jet happens to be aimed in our direction, the effects of special relativity cause the radiation to be boosted in both intensity and frequency, creating the extremely bright, rapidly variable sources we call blazars. Perhaps even stranger than galaxies with single active nuclei are those with multiple centers. These dual-cored galaxies typically result from the merger of two galaxies, each bringing its own supermassive black hole to the union. Over time, these black holes sink toward the center of the combined galaxy due to a process called dynamical friction, eventually forming a binary system orbiting their common center of mass. Astronomers have identified numerous galaxies with dual-active nuclei, where both central black holes are simultaneously feeding on surrounding material. These systems provide natural laboratories for studying how supermassive black holes interact with each other and with their environments during galaxy mergers. They also offer insights into the growth of black holes over cosmic time, as many of the largest black holes in the universe likely grew through mergers with other black holes. The ultimate fate of these black hole pairs is one of the most fascinating questions in modern astrophysics. Theory suggests that after orbiting each other for perhaps millions of years, they should eventually spiral together and merge, releasing an enormous amount of energy in the form of gravitational waves, ripples in the fabric of space-time itself. Such black hole mergers are among the most energetic events in the universe since the Big Bang, converting as much as 5% of the black hole's mass directly into gravitational wave energy. Recent detections of gravitational waves from merging stellar mass black holes have confirmed the reality of this process for smaller black holes. Future space-based gravitational wave observatories should be able to detect the mergers of supermassive black holes, providing a completely new way to study these extraordinary events at the hearts of galaxies. Not all unusual galactic centers involve active black holes. Some galaxies harbor what are called nuclear star clusters of extreme density or unusual composition. These dense collections of stars at galactic centers can contain millions of stars, packed into a region just a few light years across, creating stellar densities millions of times higher than in our solar neighborhood. In some cases, these nuclear star clusters show evidence of multiple generations of star formation, with both ancient stars and stars formed quite recently. The presence of young stars so close to a supermassive black hole poses a puzzle, since the intense gravitational tidal forces in such regions should make it difficult for gas clouds to collapse and form new stars. Yet somehow, star formation has occurred in these extreme environments, perhaps triggered by the collision of gas clouds, or by gas flowing inward along the galaxy's bar structure. Other galaxies show evidence of recent explosive events at their centers. Radio observations reveal enormous bubbles or lobes of energetic gas extending outward from some galactic nuclei, suggesting that an enormous release of energy occurred in the relatively recent past. These structures might be the aftermath of a particularly intense episode of black hole activity, or perhaps even the result of a tidal disruption event, where a star wandered too close to the central black hole and was torn apart by tidal forces. Some galaxies have cores that appear to be nearly empty of stars, so-called cored galaxies, in contrast to the more common cuspy galaxies, where stellar density increases smoothly toward the center. These cored galaxies are thought to result from the merger of two galaxies with central black holes. As the black holes orbit each other before merging, they fling away nearby stars through gravitational slingshot effects, hollowing out the center of the galaxy. Still other galaxies have counter-rotating cores, where the stars in the very center orbit in the opposite direction from stars in the surrounding galaxy. These strange configurations likely result from galaxy mergers, where the incoming galaxy had a rotation opposite to that of the larger galaxy it merged with. The stars from this smaller galaxy ended up concentrated at the center, preserving their original direction of rotation even as they became incorporated into the larger galaxy. Perhaps the strangest galactic hearts of all are those found in what astronomers call ultraluminous infrared galaxies, or ULIRGs. These systems, typically the result of major mergers between large, gas-rich galaxies, feature galactic centers where massive amounts of gas have been driven inward, triggering both intense star formation and active black hole growth. The result is a galactic center that is both shrouded in dust and extraordinarily luminous, emitting most of its light in the infrared part of the spectrum. As the dust absorbs the visible and ultraviolet light from young stars, and the active black hole then re-radiates it at longer wavelengths. In the most extreme ULERGs, the central regions can be forming stars at rates hundreds or even thousands of times greater than in our Milky Way. At the same time, the central black hole may be growing rapidly, perhaps eventually becoming visible as a quasar, once it has consumed or blown away the surrounding shroud of dusty gas. These systems offer glimpses of what many galaxies may have experienced in the early universe, when both star formation and black hole growth proceeded at rates far higher than those typically seen today. The diversity of galactic centers reflects the complex evolutionary histories of their host galaxies. Each unusual core tells a story of past interactions, mergers, bursts of star formation, and episodes of black hole growth. By studying this variety, astronomers can reconstruct the life cycles of galaxies, understanding how they have grown and changed over the billions of years of cosmic history. But this diversity also raises profound questions. Why do some galactic centers harbor actively feeding black holes, while others, like our Milky Way, remain relatively quiet? How do episodes of nuclear activity affect the evolution of the surrounding galaxy? What determines whether a galaxy will have a densely packed nuclear star cluster, a rapidly rotating disk of young stars, or a core nearly empty of stars? The answers lie in the complex interplay between different physical processes, from the large-scale effects of galaxy mergers to the microscale physics of gas cooling and star formation. They also depend on the particular history of each galaxy, the chance encounters it has experienced during its billions of years of existence, and the timing of those encounters relative to the galaxy's internal evolution. Our journey is coming to an end. We have traveled inward, through layers of stars and gas and dust, past the crowded nuclear star cluster, to the very heart of a galaxy. We have contemplated the invisible giants that anchor these cosmic cities, the ancient stars that orbit them, and the flowing rivers of gas that feed both stars and black holes. Now, as we prepare to withdraw, to return to our everyday perspective, let us pause for a moment of quiet reflection. Every galaxy turns. This simple fact contains within it a profound truth about the nature of cosmic structures. They are not static, not frozen, but in constant motion. The spiral arms of a galaxy rotate around its center, but not as a rigid body. Instead, stars closer to the center complete their orbits more quickly than those farther out, creating a differential rotation that winds the spiral structure ever tighter. Yet somehow, through mechanisms still not fully understood, the spiral pattern persists over billions of years. In that turn, that rotation, galaxies carry a rhythm. It is not a rhythm we can hear with our ears, for space is nearly empty and sound cannot propagate across the vast distances between stars. But it is a rhythm we can see in the orbital periods of stars, in the flow of gas, in the timing of bursts of star formation or nuclear activity. And it is a rhythm we can feel, at least metaphorically, in the steady, unhurried pace of galactic evolution, a tempo measured not in seconds or minutes, but in millions and billions of years. At the center of this rhythm, at the heart of this turn, is a pulse, not a literal heartbeat, of course, but something analogous, a center of mass and energy that influences everything around it. The supermassive black hole at a galaxy's center, with its enormous gravitational field extending outward through the galaxy, is something like a heart. It doesn't pump blood, but it does regulate the flow of gas, influencing when and where stars form, when and how the galaxy grows. This metaphor of the galactic heart is more than just poetic fancy. It captures something essential about the role these central regions play in the life cycle of galaxies. Just as a human heart both sustains the body by pumping blood and responds to the body's needs by adjusting its rhythm, the center of a galaxy both stabilizes the galactic structure through its gravity and responds to the galaxy's evolution, growing as the galaxy grows, sometimes flaring with activity when new material arrives from galaxy mergers or internal gas flows. There is something deeply meaningful in recognizing these parallels between cosmic structures and living organisms. Not because galaxies are alive in any biological sense, but because both life and galaxies are complex systems, shaped by fundamental physical principles, by the flow of energy and the force of gravity, by the interplay between order and chaos, stability and change. As our journey comes to a close, we return to our original perspective, looking up at the night sky from our small planet. The center of our own galaxy is hidden from our direct view, obscured by the dust that fills the galactic disk. But it is there, some 26,000 light-years away in the direction of the constellation Sagittarius, a region of extraordinary density and activity that we can detect through radio telescopes and infrared observations. You may never visit the center of a galaxy. The distances are too vast, the environments too extreme for human presence. But in a very real sense, the galactic center is with you. Its gravity holds your orbit, shaping the path that our Sunday traces through space, and thus the path of Earth and everything on it. The gentle tug of the Milky Way's central black hole, propagated outward through the gravity of intervening stars and gas clouds, has influenced the course of our planet since its formation billions of years ago. The galactic center holds your sky. The stars you see at night, scattered across the darkness in seemingly random patterns, that ancient civilizations, connected into constellations, are not randomly distributed through space. They are predominantly stars of the Milky Way, and their positions in our sky are the product of our particular vantage point within the galaxy, a perspective shaped by our distance from the center and our location within the galactic disk. Though the center of our galaxy is hidden behind dust and distance, though we cannot see it directly without specialized telescopes, it is always there. It was there before the Earth formed, before the Sunday ignited, before the Milky Way took on its current spiral form. And it will be there long after our Sunday has exhausted its nuclear fuel and swollen into a red giant, long after Earth has become uninhabitable, long after humans have either perished or found new homes among the stars. There is something both humbling and reassuring in this perspective. Humbling because it reminds us of the vastness of cosmic time and space, of how small and brief our lives are when measured against the age and size of our galaxy. Reassuring because it places us within a larger structure, a cosmic context that has endured for billions of years and will continue long after we are gone. As we contemplate this cosmic perspective, we might find in it a kind of peace. The galactic center, with its ancient stars and its quietly massive black hole, has witnessed the entire history of our species, indeed the entire history of life on Earth, with a kind of detached serenity. It neither knows nor cares about our brief lives, our triumphs and tragedies, our hopes and fears. Yet paradoxically, there is comfort in this cosmic indifference, in being part of something so much larger and more enduring than ourselves. Sleep now, beneath a galaxy still spinning. The night sky above you is not merely a scattering of distant lights, but a window into your cosmic home, a spiral galaxy turning silently around its dense, bright core. Each star you see is bound in orbit around that common center, as is our Sunday, as is Earth, as are you. We are all caught in the same gravitational embrace, all part of the same vast, complex structure that has evolved over billions of years of cosmic time. And know, as you drift towards sleep, that at the heart of this galaxy, something waits, not with consciousness or purpose, but with the patient presence of enormous mass warping the fabric of space-time. The supermassive black hole at the center of the Milky Way, Sagittarius A star, sits in near-perfect darkness, invisible to direct observation, yet profoundly influential on everything around it. It is both the physical and metaphorical heart of our galaxy, the center that holds everything else in its gravitational embrace. In this embrace, in this steady orbital dance, around a common center, there is a kind of cosmic harmony. Not the literal harmony of sound, for space is silent, but the mathematical harmony of orbital resonances, of gravitational influences balancing each other across vast distances, of complex systems finding stable configurations that can persist for billions of years. It is the harmony of a galaxy in equilibrium, neither flying apart nor collapsing inward, but maintaining its spiral structure as it rotates around its dense, bright core. As your consciousness fades towards sleep, let your imagination expand outward, beyond the confines of your room, your home, your planet. Imagine yourself as part of this vast cosmic structure, this spiral galaxy with its billions of stars, its flowing rivers of gas and dust, its central black hole anchoring everything else in its gravitational field. Feel the slow, stately rhythm of galactic rotation, the pulse at the heart of the Milky Way, the center that holds your sky, your orbit, your cosmic home. Sleep now, beneath a galaxy still spinning, and know, at its heart, something waits.